Yes. So let us start. Uh, first I wanted to ask, has everyone received my email? Yeah. Uh, hmm? What do you mean? I'm not streaming it in real time. I'm recording it and putting on YouTube. And so, do you think it's better to stream it or is it fine like this? Uh, so the first lecture is there. So, uh, okay, so this lecture is about classification of second order PDEs. Partial differential equations with constant coefficients. So uh, we want to study an equation that has the following form. So since it's of second order, it contains the main part with some symmetric matrix Bij times d in dx I, d in dxj. Maybe I'll better use the proper notation, since I will use a parenthesis for this axis and the upper indices for this matrix. So these derivatives act on our independent function. Then, in principle, we can have a first order. So this ij go from 1 to n. And then we have some linear term plus some of ai d in dx I ai time acting on u plus some constant times u equal to 0. And so another form to write this equation is to do something like this. Say that it is this, well, it would better to use. Let us use notation nabla for this vector of partial derivatives. And in terms of this nabla, and this can be written as nabla transposed times matrix B acting on nabla plus scalar product of pairing between A and nabla plus C. All this acts on U and gives 0. So it's on the same equation. And now we want to. So what does it mean to classify these equations? It always means that we need to classify them up to some transformations, and these transformations are the following. So the most obvious transformation is that we can perform some change of variables. We can say that xi's are xi's that depend on some new variables of the whole collection of variables x1 tilde and so on xn tilde. Another transformation that we can say that dependent function u is some rescaled function, no, not rescaled, but some new function u tilde times some, let us write it like this, exponential of some f of x1 and so on xn. There are two main transformations. Of course, we can also multiply all this matrix vector and constant by some function or by some constant, and it keeps the equation the same. But actually, not need this transformation. It's all the same because one set of variables is expressed in terms of another set of variables. And now we want to study what happens with such kind of equations, actually with any differential operators, when we perform such changes of variables and of functions. So let us first study this change of coordinates. And to do this, let us introduce such thing as algebra of differential operators. Yeah. So first of all, we have some algebra of functions. So we have functions on Rn, which can be, depending on what we want, what we are interested in, it can be either some smooth functions, for example, C-infinity functions or Rn, or they can be some polynomial functions, polynomials of x1 and so on, xn. So it's so I will not specify precisely what kind of functions they are. But they can be whatever functions we want. So it's one ingredient, and another ingredient is the algebra. So another ingredient is the vector space generated by differential operators. So maybe how to write it better. So we have n generators that we want to add to this algebra. So d1 and so on dn, which means d in dx1, d in dxn. So this d1 is d in dx1, this dn is d in dxn. So what is the algebra? What in this algebra? This algebra, which I can denote A, and there is some better notation, but it is just this algebra of functions of R on Rn extended by derivatives, by derivative operators. So, in a sense that elements of this algebra have a form like some constant, some function of x, of x's. Maybe I can write it like this, plus some a first order differential operator, C1 I x d I. Maybe better to solve this notation. I plus c 2ij di dj plus and so on. And it's a trivial exercise to check that the subjects actually form algebra. And to do this, we need to perform one simple computation. We need to permute a derivative operator with operator of multiplication by some function. So suppose that we have some operator di and we have some function f that depends on all these x's.
All the terms, the generic terms, is implicit sum over the indices?
Yes. I'm well, probably we will not use this notation in the future, so I'll simply write that there is sum. Yeah, sorry. Probably. So everywhere else, I wrote it basically. Yeah, so if we're working with many such expressions, then it would be better to introduce such notation, but okay, it's not needed. So suppose that we have some function and some differential operator, which is derivation in the ice variable, and we want to study this object. So this is an operator of multiplication by this function. And let us act with this construction on some test function, phi of x. So we first multiply it by f of x, then act with derivative in ice variable. And let us compute this expression. So this derivative will act on both functions, on the original test function and on the function we multiplied it with. So we need to multiply. We need to differentiate both of them. So it will be di f of x, where this maybe let me write it explicitly. Di f of x and dxi times phi of x. It's one term. Another term is when we differentiate phi of x. So plus f of x d phi of x in dxi. So we can write this in the following way: that it is df in dxi plus f of x times di. All this acts on phi of x, and this works for any phi. So if you compare this term here and this term here, we can write a relation in this algebra that di times f of x equals to f of x times di plus well, I can write it in a condensed form, dif of x. It means that this function is differentiated, and it is a function, and this object is a differential operator on the first order. So there is this relation, and one corollary of this relation is the following: that so it is a kind of additive relation. We can write its multiplicative form. So maybe I can rewrite this relation using commutator. So if you introduce a commutator in this way, that commutator of A and B is AB minus BA, then this relation is rewritten as a commutator of DA, DI with F of X is equal to DIF of X. So commutator of a differential operator as a function is a function. And in this way, we can turn this algebra of operators into Lie algebra. If not multiply them, but just take commutators. And also one remark that this commutator has properties very similar to properties of derivative. Namely, we can check the following identity: that if we compute the commutator of A with product of two whatever objects, some differential operator or matrices, then it equals to commutator of AB times C plus B times commutator of A with C. And this should be compared with a property that a derivative of product of two functions is this, that di of di f times g, maybe let me write it simpler, f times g prime equals to f prime g plus f g prime. So, and the operation that satisfies this property is called derivation. So it can be, and you see that it can be either a derivative or some commutator with something. So, okay, so it was one way to write this relation, but there is another way. It was a kind of commutator in the algebra, but there is a kind of commutator in a group. Namely, I propose to consider the following expression: e to f of x times e to minus f of x times di times e to f of x. So let us rewrite this expression using this relation. It will be just di because these two exponentials cancel. In this first term will be di plus in the second term when we differentiate this exponential. So is clear? So this relation will be useful for this second transformation when we multiply a dependent function by some function of x's. And this relation will be useful now. So what I want to do with this, we can write this relation for some simple functions, namely for coordinate functions themselves. And it has the following form then, that commutator of di with xj. So who can tell what it equals to? Yes. Minus xj times. No. So, why do you think that there should be something else except delta ij? Oh, it's just this. We differentiate j's coordinate function in xi, and it can be either a 0 when it is different function or 1 when we differentiate xi in xi. So. So maybe I will erase this. Okay. I now suppose that we want to. Are there any questions about this? So, do you have any questions, or is it fine? No. But what second term?
Well, there's not a second term.
So, in which formula? There was this formula, but we can write these two terms as a commutator. Like,
I'm talking about the one with the delta function.
hmm?
The delta.
But what can be this, what could be another term?
Well, it's a commutator, so it's AB minus PA.
Yes. So, uh, let us write this. So it is di xj minus xj times di. Right? It is operator of multiplication by xj. It's operator of derivation in xi. And here they are multiplied in the opposite order. So in computations we have done previously tells us that this derivative operator can be permuted with xj, and the difference will be given by derivative of this xj. So it equals to what? It equals to xj times di plus di of xj, yes, in the second term. Mm, minus this second term that was in this commutator. So these two cancel, and you consider commutator precisely to make them cancel.
The set function of n has to be only a vector space or field?
Well, if ask it to be a field, then we need to know how to invert functions, and functions can have zeros. So we either allow functions that have poles somewhere. It is fine. If they are, for example, complex analytic functions. Otherwise, we can treat it as just a ring that, yes, and that we can multiply functions and add them, and it is sufficient for our purposes. And if you write something like this, then this exponential is definitely non-zero, so it's invertible element of a ring. So.
And when we add this operator, we say that is an algebra.
Yeah.
A ring plus this operator is an
algebra. Well, it's maybe. I don't know if there is some fixed terminology. We can. So originally it was some commutative ring, and after we had these operators, it became non-commutative. So maybe yes, maybe we can call it algebra. Maybe we can call it non-commutative ring. Maybe it's better. It's better call it algebra. So. So. Yeah, and let's finish this computation. And here we have derivative of xj in xy, and this is delta ij. So, by the way, this is called AVL algebra. The algebra generated by x's and di's. So. Okay, so are there any questions? So let us see. Let us see what happens if perform a linear transformation with this axis. We can do this with nonlinear transformation, but let us consider something simple. So we write that x is equal to some tij x j tilde. So this is a change of variables. And we want to extend this to the full algebra automorphism. So this commutation relation should be preserved. So we try to guess what happens with derivatives. So let us say that they transform with some other matrix. So let us say that derivatives are transformed like this. So it is some matrix T prime, T hat, Ji, Dj, Dj tilde. And we know that commutation relations in both algebras are the same. In the sense, dj tilde with xi is again delta ij. And we want to write commutation relation in the original algebra. So di, delta ij equals commutator of di with x di with xj. And again, sum over j, sum over j. So here we have some t hat. And here we have sum over some L. T. So let us now compute this commutator. So it gives delta Kronecker of K and L. So it is sum over K and L, T, K, I, delta KL, T hat, JL. So we can remove one of the two indices and get sum over sum over K, for example, T, J, K, T, so T hat, T, K, I. So it is just a matrix product. So we can write that it is T hat times T and we take indices in Ji of this matrix. But we know that matrix elements of this matrix are matrix elements of identity matrix. Therefore, T hat times T equals to 1, and therefore T hat equals to T inverse. So so we see that if we perform some linear change of coordinates, then it corresponds to a linear change of derivative operators with the inverse matrix. And I wrote this commutator not just to get this formula, but also to show some a practical way to compute the complementary transformation. In the sense that we can find some linear transformation of derivative operators, and if we want to see what happens with coordinates, or vice versa, we can simply check that their commutators are like this. They commute on delta chronicle. But the main outcome of this computation is that we are actually allowed to perform any linear transformations with derivative operators. So, and we can use it for bringing our differential operator to some nice form. So this is the first thing we need to remember.
So now, for that instruction, we are imposing the transformation to be inverse of the other.
Yes, of course. So it was our original guess. We just need to fix what this matrix hat is. And of course, this can be derived from the usual calculus, because if you want to compute a derivative of some function that depends on some changed coordinates, then we can use a chain rule to express this derivative in terms of derivatives in this new tilted variables. So this can also be done, but this is probably a little bit simpler from mnemonical purposes. It's easier to remember. Okay, so are there any questions? So so it was one a useful transformation, and let us find another useful transformation that comes from this formula. So let us choose this f of x to be a linear function of x. Just insert some alpha x and di e to alpha x. So what do you think? What will be the result of this conjugation of di?
Alpha I times.
Oh yes, we do have alpha I, and what else? Do you mean di as derivative?
Yes,
Oh, I call it d. So yes, it's derivative. because it's this term is simply this di of f, and this term is well, it is the derivative that we had originally. Mm. Uh, and if we conjugate the full vector of derivatives, which denoted nabla, it will be nabla plus alpha. So So we have this tools. One is that we can perform linear transformations with this vector of derivatives. It can be written equivalently as mm, mm, that this vector nabla equals to uh, mm, uh, nabla tilde times T inverse. But it doesn't matter. It's just another way to write the same formula. So we can perform arbitrary linear transformations with this vector of derivatives, and we can also shift it by some constant vector. And this looks very similar to what we have in geometry, where we have some classification problem of quadratic surfaces. So it's essentially the same problem, and the answer will be the same. So there we also had this possibility to shift coordinates, of course, and we could perform linear transformations. So. Are there any questions so far? So, yeah. Let us try to perform these transformations with our differential equation. So or maybe better to say with our differential operator. So we have this differential operator that is nabla. Well, there is this quadratic form b times nabla plus a times nabla plus c. So, do you know, do you remember what is the classification of quadratic forms under such transformations? Like, what are the canonical forms we can bring any quadratic form to? Mm-hmm. And probably with zeros, because no, yeah, thanks. So, so we start from this generic differential operator, and at the first step, so step one, at this first step, we find such a transformation of coordinates that find this transformation such that this matrix becomes canonical, in the sense that this B tilde in the new equation will equal to 1, -1, and probably zeros. So this first block of size, I don't know, P, Q, N minus P minus Q. So it was the first step, right? Now the second step. Maybe I can write it here. So in the second step, we have this matrix with ones, minus ones, and zeros on the diagonal, and side by side, we have a vector A. And let us see what happens with this matrix and this vector when we perform this kind of transformation with coordinates. So in the second step, we find we can say that there is a new differential operator that is obtained from this differential operator by this conjugation. So d tilde is obtained from d by e to alpha x times d times e to minus alpha x times e to alpha x and when we do this, we can say, of course, this transformation, this conjugation acts on each individual differential operator, because we can make the following trivial remark that if we apply this transformation to product of two derivatives, di times dj e to alpha x, then we can insert another a pair of exponentials between these derivatives. Write it like this: minus alpha x di e to alpha x e to minus alpha x dj e to alpha x. So, who can tell what it is, what it equals to? So we can compute this expression separately for each of these terms, for di and for dj. And we know that this action on di gives just shifted by alpha I. So it will be di plus alpha I. And this will be dj plus alpha j. So this is algebra automorphism. If you perform this conjugation with any element in this algebra, it reduces to conjugation of each term in this element in this product. So it simplifies all partial derivatives and shifts them by corresponding alpha i's and alpha j's. And this conjugation appears, of course, when we try to multiply our dependent function by e to alpha x. So maybe we can look at this in more detail in some simple example. But now let's just see what happens when we conjugate this differential operator with this exponential. So basically, as I said, that it shifts all numbers that appear there by alpha. So we have this quadratic form, and it turns into nabla transposed plus alpha transposed b nabla. And well, this b is simplified. It has only ones and minus ones. Nabla plus alpha. Then we have a nabla plus alpha. Actually, it's some a tilde because it is already transformed somehow. Plus constant c. And let us go to the next blackboard. So now we can open all those brackets in the quadratic form and get a quadratic form of nabla plus, since it is symmetric, then the two terms linear and alpha will be the same. So we have two so maybe it's even not necessary to write transposed because it's a scalar product between two vectors. So I can omit it easily.
What is
It is something that we get after this linear transformation of axis. So actually, this number should be number tilde because it is now in this new variables. Yes. So sorry. Yes. We changed variables and we had to change all other objects here. So.
And this is the how we are searching for this kappa vector.
But this is what we are doing now. In a sense, suggest some angles that something like this should be done to this differential operator. And now we can choose this vector in a way as we like. So basically, I would like to kill as many components of this vector A as possible. So let us look at this term. So it will contain nabla times a scalar product with b tilde, and it's again nabla tilde. So b tilde times a tilde. Oh, sorry. B tilde times alpha. Plus one more term with alpha b tilde alpha. So this is basically a quadratic form expanded in alpha. And then a tilde nabla plus a tilde alpha plus c. So we would like to do something with these terms. So ideally we would like to get rid of them, but let us check whether it is possible. So we have side by side. So we have side by side two expressions. To b tilde times alpha plus this vector a tilde. And they look in the following way. So this one is 1, 1, 1, minus 1, and then zeros. And there is some vector alpha 1, alpha n is 2 plus a So you see that this first p plus q components of this vector alpha can be adjusted such that first a p plus q components of vector a are cancelled. So we can make it equal to 0, 0, 0. Then a p plus q plus 1 a n. And to do this, we choose alpha 1 equals to minus 1 over 2, alpha p plus 1 equals to a p plus 1 over 2, and so on. But these components are not affected. So in principle, if we had a quadratic form with their eigenvalues, we can still have some non-trivial vector in the second component. So what can we notice now? That if p plus q equals to 0, if p plus q equals to n, yes, and there are no eigenvalues, then this classification is over, because we have a quadratic form. So how to write this? So there is option 1. P plus Q equals to N. So in this case, this operator attitude becomes yes, okay. Yes, so do you have any questions after the break? Or, okay, so let us proceed maybe. Uh, so one option is where the rank of this matrix is full. There are no zero eigenvalues, and so this new operator is given by just delta 1 d1 to the squared plus dp to the squared plus minus dp plus 1 tilde squared minus d tilde p plus q squared. And we had some constant from the very beginning, and we see that this constant gets some extra corrections from this term, so it will be something. So it will be some constant which can be either 0 or non-zero. It can also be positive or negative. So so there are some options depending on the value of this C tilde. So have something like 1, 1 when this constant is 0. So this differential operator is just so it is, and so it is a kind of wave equation in the space-time with signature PQ. Examples that are interesting and useful correspond to cases when P equals when Q equals either to 0 or to 1. So Q equals to 0 is a Laplace equation. Q equals 1 is the wave equation. And of course, there are other options, but we will not study them. So it was option 1. Another option is that this constant turns out to be non-zero. 1, 2. C tilde is non-zero. And of course, we can change the overall sign of this differential operator because it will be the same equation. And it will just change P and Q. So we can assume by the generality that C tilde is greater than 0. So in this case, it seems that this equation has some parameter, but actually no, because we can do further scaling of variables by saying that this odd variables x xi tilde equal to some xi with 2 tildes divided by square root of c, or of c tilde. And if we do this, then this differential operator, d tilde, will equal to c tilde times d 2 tildes 1 squared plus something minus d p plus 1 with 2 tildes squared minus d with 2 tildes p plus q squared plus 1. So it's almost the same differential operator, but with a constant term. And this, so this constant term can be either 0 or 1. It can always be brought to one of these two values. So this equation, again, depending on signature, it can be either a Helmholtz or Klein-Gordon equation. Right. So any questions about this? So this was when p plus q equals to n. Let us see what happens when there are some zero eigenvalues on this quadratic form.
This is a random question, but we know the Klein-Gordon equation is the same as the Klein-Pavlo topology.
No, they are related only by the name of, well, actually, no. I'm actually start wondering if it wasn't the same plane. Probably he was, but I'm not completely sure. Oh, but the objects themselves have no relation to each other. Okay, so now we have option 2. When p plus q is less than n. So in this case, a result of this procedure will leave us with some vector with some non-trivial components at the end. So this a tilde will equal to 0, 0 and something. A tilde. So this vector can be called a tilde. Well, maybe it had tilde at the very beginning, so now it has two tildes. Oh, maybe one tilde. So we call this vector a with two tildes. So this vector a with two tildes has some components from p plus q minus 1, plus 1 to a tilde n. And b has the same form. So a question to you. What do you think about this vector? What can be its canonical form? So like, how can we simplify it by changing x coordinates? So a reminder is that this are first p coordinate, this is first q coordinates, and this non-zero components of vector a with two tildes correspond to the last block of quadratic form with zero eigenvalues.
Maybe we can reduce non-zero terms and bring it to 1.
To one in just one place, right? Yes, so there is an option that this vector was 0 from the very beginning, and in this case it will stay 0. But if it was non-zero, then we can bring it to form 1, 0, 0, 0, 0, because any two vectors in this n minus p plus p minus q dimensional space can be brought to any other vector. So all the vectors of vector space are equivalent, except 0. So well, there is no, maybe I can denote it as a third step of classification, and there are again two options. To 1, when this vector was 0. So in this case, we will get the same differential operator plus constant. So d tilde is d1 tilde plus something minus d tilde p plus 1. So squared. So it's essentially the same situation as we had before, with only difference that there are some extra variables from p plus q plus 1 to n that simply don't enter this differential operator. So our equation is just a collection of equations for different values of those variables. So it can be solved differently for in each slice of this space. But on each of the slices, this equation is essentially equivalent to what we studied before. So we can simply say that it is inside our classification up to this extra stupid variables. It don't enter a differential operator. Yes. So the only interesting situation is the second one, 2, where this a tilde does not equal to 0. In this case, we can find another transformation of x's, introduce some x with 2 tildes. Equal to some tilde t, I don't know, t tilde times x tilde, or just some next change of coordinates, such that this new vector a with 3 tildes is equal to 0, 0, 0, 1, 0, 0, 0. And this happens at position p plus q plus 1. So far our differential operator looks like this. D tilde is d tilde 1 squared plus something, then minus something. Then plus d tilde p plus q plus 1 plus c tilde. But now we can notice that this c tilde can simply be combined with this last derivative, and we can say that this altogether can be obtained from a conjugation of derivative in p plus q plus 1 variable by exponential that depends on this c tilde. So we can notice that it equals to e to c tilde times x tilde p plus q plus 1 minus times d plus q plus 1 e to c tilde x tilde p plus q plus 1. So it means that this c tilde can also be reduced. So, and finally, the canonical form of the differential operator is d with 2 tildes equals to d1 tilde squared plus and so on minus d tilde p plus 1 plus d tilde p plus q plus 1. So it is a kind of heat-like equation, because in principle we have different signs in this quadratic part. And heat equation has only positive signs, but we also get this. So And again, here we have some extra variables that don't enter this equation. Uh, mm, uh, uh, and we neglect them. So, so, so it's the end of classification. Mm.
So are all the equations that we talked about in the last class kind of like the canonical forms of what you get if you just add constant coefficient partial differential equations and then transform them to the simplest representation?
Yes. So we obtain, sometimes we obtain them with some trivial coefficient that could be removed by changing coordinates, but essentially yes. And so this is an explanation why we have so few of these equations, because all the space of second order differential operators of in n variables is a union of finite number of orbits of these operators. So they don't have any parameters. They don't have any continuous parameters. They can be described by this signature of quadratic form, and then by the value of free term, like better to say by the type of this last term. It is either zero or constant or some first derivative that gives a heat equation. So, so it's the end of classification. Maybe one remark about this transition that we used several times. So we had this transition that d tilde was e to minus alpha x d e to alpha x. Let me tell in more detail what it means. So suppose that a differential operator d was a Killing function u. So d acting on u was 0. Then if you take function e to minus alpha x and act with, on it with d tilde, so you can write like this. So let us write all this. So these two exponentials cancel, and we have operator d acting on u. So this is 0. So this change, this conjugation of differential operator by exponential corresponded to this change of dependent function. We simply multiplied them by a linear exponential, and it is a solution of a new equation. So let us now see how all this works in some simple example. And maybe let us even try to solve the equation we get in this way. So are there any questions about this classification? No. Hmm?
We used algebra to constrain and find all the possible canonical equations. Has it been done with if you allow the derivatives to be fractional instead of 1 and 2 and 0, you
No.
go 0 up to 2?
But I don't expect any reasonable answer in that case, because even here, if I allow cubic differential operators, we get immediately some huge number of invariants of these cubic forms, which are just numbers, and they cannot be removed by these transformations. So
you restrict it to between 0 and 2, and not go above 2, but allow the non-integers.
But what is, for example, a result of transformation of some fractional derivative? Like if you simply take some coordinate rotation, it will be some unclear operator, because I would say that in that case, operator itself breaks very basic space-time invariance. Because if you consider the symbol of this operator, for example, if if you have something like dx squared plus dy squared, then we can switch to something like px squared plus py squared, and constant curls of this function are just circles, so they have rotational invariance. And so we can expect something. But if you take something like dx to power 1/2, maybe 1/2 py to 1/2, then how does it look like? I think it should be something of this kind. Surface of a constant level of this function. So it has some preferred directions from the very beginning. And we have almost no transformation that are allowed in this case. So you can write this, and if you add something else, then we'll have no freedom to transform that part of a differential operator. So don't expect anything good. Okay, let us consider some simple example. let's take this operator. So it can be written as dx squared plus 2 dx dy minus 2 dy squared acting on u equals to 0. Then, so we need to perform this coordinate to derivative transformation that brings a quadratic form to canonical form, and this can be done algorithmically in the following way. We take the first variable we like, and it should be such variable that has a non-trivial quadratic part. So it should be dx squared. And we complete this variable to, so we gather all linear terms that contain this variable to full square. So we write like dx plus dy squared. So we collected this first term with a y derivative, and we need to subtract this dy squared. Maybe let me think if I like this equation or not. Maybe. Well, I probably don't. No, let us leave that part. It's fine. Maybe let us make it 3 to make number nicer. So we can transform the first part in this way. Then minus 3 dy squared. And all this acts on u. So it equals to 0. So it can be written now as dx plus dy squared minus 2 dy squared acting on u equals to 0. So we see that it is the wave equation, and if you want to find the inverse transformation, no, let's say not inverse transformation, but transformation of x's, we need to do what? We need to say that this variable is, so this derivative is dx tilde, this derivative is dy tilde, and we need to find x tilde and y tilde. So we need to say that dx plus dy acting on y tilde is 0, dy acting on x tilde is also 0. And there are two other equations that dx tilde acting on x tilde is 1. on x tilde is 1, 2 dy acting on y tilde is also 1. So let us solve the system starting from equations that give 0. So if dy of x tilde is 0, it means that x tilde contains only x. And if dx plus dy acting on x tilde gives 1, that it means that x enters with coefficient 1. So x tilde is x.
How did you get the second set of equations on the right?
Because dx tilde acting on x tilde should give 1. Yes. So x tilde equals to x. And now about y tilde. So this equation tells us that y tilde contains x and y with opposite coefficients, because this combination of derivatives kills it. Y tilde equals to, let us write y minus x with some unknown coefficient. And if you look at this equation, we see that this coefficient should equal to 1/2. So we can see, of course, that this matrix that transforms derivatives is inverse to this matrix, but sometimes it's easier just to get transformation that compute this matrix inverse explicitly. And so this was about canonical form of this equation. But the funny thing about 1 plus 1 wave equation is that it is super easy to solve. And in principle, we can start from this canonical form, but let us do this with our original equation. In a sense, there is another canonical form for this special case, which is even better than this difference of dx squared minus dt squared. So we can write this difference as a product of sum and difference. So dx plus 3 dy times dx minus dy acting on u equals to 0. So now we can say that this derivative is dxi, and this derivative is d eta. And our wave equation now has the form, xi and eta should be found. But they are basically some indifference of this x tilde and y tilde. So now this equation has a form that d xi d eta of u equals to 0. And this equation can be solved. Because first, if you see that some function is a function of so if you see that a derivative of some function of eta and psi in psi equals to 0, we know that this function is a function of eta only. So solution. D eta of u is some f of eta. And then what can we say about u itself? So let's use some big F. So eta is some function that depends on both eta and psi. Oh, so u is a function that depends on eta and psi.
Is there any symmetry?
Oh, but why do we care about symmetry? Oh, of course there is symmetry that we can change eta and psi to arbitrary function of eta and psi. But I'm asking a simple question from calculus. Like, what is the generic solution of such equation?
A
What do you mean?
a normal distribution?
No, what do you mean by normal distribution? There is a function of two variables. We know that if we differentiated one of these two variables, we get some function of just one variable.
What's the first order I forget how to say that letter. Psi.
No, why first order? An arbitrary function of psi differentiated in eta gives 0.
We get the interval of f from a constant but with respect to eta, so it's a function of c.
Yes, and since this f was arbitrary function, we can just introduce another function for integral of f and say that u of eta and psi. So eta and psi is a sum of two functions, f of eta plus g of psi. And now if you substitute it back to this equation, then it's clear that it is actually 0, because this combination of two derivatives in e times psi kill each of these terms, because its derivative is 0 either in eta or in psi. So and we have proved that it is the general solution of this equation. So we see that this 1 plus 1 wave equation is super simple, and you can try to find what this xi and eta are. Try it in terms of initial coordinates. Actually, in this simple case, we will see that it's important to have a negative sign between two second derivatives, because if we had a positive sign, then in principle we could do the same trick, but in this case we would need to take some combinations with complex numbers, and it will correspond not to just functions, but to homomorphic and anti-homomorphic functions. So and they are much more restrictive than just functions of a real variable. So we'll study it later, but some remark about the general situation. But all the signs in quadratic forms matter. And each of these equations should be treated independently. And also dimension of the space-time matters because this simple solution to the wave equation is available only in 1+1 dimension. And so are there any questions about this? So I will add several problems about classifications of these equations. You can try to do them at home and make sure that you are able to find a type of any equation you meet. And maybe I'll add some wave equation of this kind. Okay, are there any questions? Okay, then thanks for your attention.